Okay, so now let's work on miscellaneous exercises on chapter 14, which is another 7 questions. Let's see what these are. So number 1, you want to write the negation of these statements. Right, the negation of these statements. So for example, these are actually fun when you get to know them, and well, when you know the algebra, when you understand these basically if-then statements and compound statements and how to negate them and to basically find the contrapositive and so on and so forth, then there is some algebra, there is some specific sort of algebra, if I'm not mistaken. I remember seeing that algebra somewhere years ago, and there is some algebra that works on logic. Now I don't really remember what that specifically was, but I suppose there is some sort of algebra that works on logic, and then you can put these statements, for example, this is true, this is false, and so on and so forth. You can put these true and falses into that algebra, and then it gives you, for example, whether this very complex and complicated, for example, series of truths and false and truths and false and true and false and so on and so forth. The whole thing is basically whether true or false. So that's something interesting that you might get into if you, but I suppose I don't know, maybe we will have that in the next book or not. I'm not really sure, but of course when you get into higher mathematics you might actually need to learn that probably. Now anyway, let's write the negation of these statements, which is, for example, basically statement P is for every positive real number x, for every positive real number x, the number x minus 1 is also positive. The number x minus 1 is also positive. So there is this statement says that for every positive real number x, the number x minus 1 is also positive, which is of course not true. So when you have for every, then the negation of this becomes, it is false that the whole sentence, it is false that for every positive real number x, the number x minus 1 is also positive. And then you could rewrite that as, for example, there exists a positive real number x such that the number x minus 1 is not positive or is negative. So the answer here is, let me see if the answer, I can find it. So there exists a positive real number x such that x minus 1 is not positive. So for example, that's, now I don't want to keep writing these, and of course you already have access to all of these questions answers, so I don't have to necessarily write everything down. Or there, the next basically statement is all cats scratch. All cats scratch is all cats scratch. So the negation of this would be, it is false that all cats scratch, or you can say that there exists a cat that does not scratch. So that does not scratch. So let me put this over here. So there exists a cat which does not scratch. or you have for every real number x, you have for every real number x either x is greater than 1 or x is less than 1. Either x is greater than 1 or x is less than 1. So for every real number x, either x is greater than 1 or x is less than 1. So you can say that to negate this, you can say that it is false that for every real number x, either x is greater than 1 or x is less than 1. And then you can rewrite that as there exists a real number x that basically where basically x is well, not greater than 1 and not less than 1, which is x is equal to 1, I suppose. That's the only possibility, I suppose. So you could say there is a real number x such that x is equal to 1, I suppose. So the answer is there exists a real number x such that neither. Okay, so they have written this as, so this is, for example, interesting. So they have written this as there exists a real number x such that neither x is greater than 1 nor x is less than 1. So you have basically neither and nor, right? Neither and nor. Instead of either or, they have used neither nor, which is actually a good idea. I couldn't think of this combination here. Or another statement that we have here is there exists a number x. There exists a number x such that such that 0 is less than x less than 1, or x is greater than 0 and less than 1. So the negation of this would be, it is false that there exists a number x such that x is greater than 0 and x is less than 1. Or you can say that there does not exist a number x such that basically this condition exists. There does not exist a number x such that this condition exists. Or you can say that for, I don't know, for every number, for all, probably, I mean, if you're talking about, for example, real numbers, I would say for every real number x. So here we have x is basically greater than 0 and less than 1. Then you could say that either x is less than 0 or basically greater than 1, something like that. Let's see what. So here they have simply written that there does not exist a number x such that condition basically is the case. So there does not exist, which is of course good enough. Now, question number 2 is state the converse and contrapositive of each of the following statements. So you have, for example, this statement here, P, a positive integer is prime only if it has no divisors other than 1 and itself. So the statement P is a positive integer, is prime, a positive integer is prime only if it has no divisors other than, it has no divisors other than 1 and itself. 1 and itself. So a divisor is basically what that means is that, okay, I need to check this. Let me see what the divisor is. I see, a divisor is basically the factor of a number. So here it says that the divisor, also called the factor of a number, is the number which divides, okay, for integers only positive divisors are usually considered, though obviously the negative of any positive divisor is itself a divisor. So basically a divisor is nothing but is the same thing as the factor. Okay. So what that means is that it says that the positive integer is prime only if it has no divisors other than 1 and itself. And that's basically the definition of a prime number. Now you want to find the converse of this and the contrapositive of this. Okay, so now this statement here is basically the same as a if-then statement, meaning that you can write this as, so only if means basically what it means is implies. Only if means implies. And then basically this part here is your, for example, P, and this part over here is your Q. This part is your Q. And this is basically nothing but P then Q. Now if you want to write the converse of this, the converse of this would be Q then P, and the contrapositive of this would be not Q implies not P. Not Q implies not P. So then the converse would be Q then P, meaning that if a positive integer has no divisors other than 1 and itself, then it's a prime integer, then it's a positive prime integer. That's the converse. And the contrapositive of that is if not Q then not P, meaning that if a positive integer has no divisors, has divisors, not we have to say that the negation of this. So if you need to say if a positive integer has divisors other than one and itself, then it's not a prime number. So so then the statement can be written as if a positive integer is prime. If a positive integer is prime, then it has no divisors other than one and itself. And the converse is if a positive integer has no divisors, the converse. If it has no, the converse is if a positive integer has no divisors other than one and itself, then it's a prime integer or it's prime. And the contrapositive is if positive integer or if a positive integer has divisors other than one and itself, then it's not prime. So, and you just need to basically follow these two and then somehow basically put it in the context that you have up there dictated by the statement. Now we have another statement here, statement Q, which is I go to a beach whenever it's a sunny day. So I go to a beach whenever it's a sunny day. So you can rewrite this as, so this is your if clause. Whenever it's a sunny day, this is your if clause, meaning that you can write this as if it is a sunny day, then I go to a beach. I suppose that's how you can write it. If it's a sunny day, then I go to a beach. Now, you can call this your P, and you can call this your Q. And so what you have here is if P, then Q, or P implies Q. Now the converse of this is if Q, then P, meaning that Q implies P, and the contrapositive of this is if not. So the statement is this thing over here, the original statement. So the contrapositive of this is if not Q, then not P. If not Q, then not P. Meaning that not Q implies not P. So now the converse in terms of an English sentence would be, the converse in terms of an English sentence would be Q then P. So that means that if I go to a beach, then it's a sunny day. If I go to a beach, then it is a sunny day. And the contrapositive is if I don't go to a beach, then it's not a sunny day. If I go to a beach, then it's a sunny day. If I don't go to a beach, then it's not a sunny day. That's basically how you write this one. We have another statement R that says if it's hot outside, if it is hot outside, then you feel thirsty. then you feel thirsty. So you can take this as your P, and you can take this statement as Q, and so you have basically P implies Q. This is your statement. Now you can write this as basically the converse of this is basically if Q then P, or Q implies P. That's the converse of this. Q implies P. The contrapositive of this statement, is if not Q, then not P. Meaning that not Q implies not P. Okay, so what that means is that then the converse would be Q then P. If you feel thirsty, then it's hot outside, and the contrapositive is if you don't feel thirsty, then it's not hot outside. That was question number 2. Now question number 3 is write each of these statements in the form if P then Q. If P then Q. You want to write in the form if P then Q. Meaning that you want to write it in the form P implies Q. Okay, so the first statement that we have is P. Statement is P. It is necessary to have a password to log on to the server. It is necessary to have a password to log on to the server. It is necessary to have a password to log on to the server. So that means that the necessary condition to basically it is a necessary condition to have a password to log on to the server. So that means that if you want to log on to the server, then you will need a password. You will need a password. That is a necessary condition. If you log on to the server, then you have a password. They have written it as if you log on to the server, then you have a password. So let me write it in the exact same way. So they have written it as if you log on to the server, you have a password. That makes more logical sense, of course. If you log on to the server, then you have a password. Now, the second statement that we have is Q, which is there is a traffic jam whenever it rains. There is a traffic jam whenever it rains. So when you say whenever it rains, that means that whenever it rains, there is a traffic jam. That means that it's a sufficient condition for this to happen. So then you can say that this is a sufficient condition. Sufficient condition. This is a sufficient condition for this to happen, right? So that means that when you write a statement as if P, then of course P is a sufficient condition for Q, meaning that when you write P implies Q, then basically then P is a sufficient condition for Q. So then you can say if it rains, or whenever it rains, there is a traffic jam. So if you were to write it using if it rains, there is a traffic jam. There is a traffic jam. So basically remember that whenever you have P implies Q, P is a sufficient condition for Q, and Q is a necessary condition for P. And we talked about this in terms of the example of those two numbers 9 and 3 and the whole condition and situation there. So that is that. Now there we have another statement here, statement R, that says that you can access the website. You can access the website. You can access the website only if you pay a subscription. Only if you pay a subscription fee. You can access the website only if you pay a subscription fee. So only when you have only if, that means that this is a necessary condition for this. That means that basically you can think of this as your, for example, as your P clause, as your, for example, the P statement. You can think of this as the Q statement. So then this means basically P then Q, or if P then Q. So you can write this as, a statement as if you can access the website, I'm sorry, no. You can access the website if you pay a subscription fee. Well, okay, that does make sense. If you can access the website, then you pay a subscription fee. Logically, it makes, in this logic, it makes sense. So you have to write this as if you can access the website. I was trying to fit that into human language. It doesn't necessarily always work like that. If you can access the website, then you pay you pay a subscription fee. Subscription fee. So this was question number 3. This was question number 3. Now question number 4 is rewrite each of the following statements in the form P if and only if Q. P if and only if, P if and only if Q. P if and only if Q. They want to write all of these statements in this form. So now if you watch television, then your mind is free, and if your mind is free, then you watch television. So the statement is basically statement P if you watch TV, then your mind is free. Then your mind is free, and if your mind is free, then you watch television. Then you watch TV. So you can see that these are, so you watch TV, your mind is free. Your mind is free, you watch TV. So then you can for example define two statements as, for example, Q, you watch TV, and statement R, you watch TV and your mind is free. So this says that this first part over here says that if you watch TV, meaning that if Q, then your mind is free. Your mind is free is R. So then R. And the second part is if your mind is free, then you watch TV. So if your mind is free, meaning that if R, then Q. So as you can see, you have if Q then R, and if R then Q. So then you can write it as, for example, you can write it as basically Q if and only if and only if R, or you can say R if and only if and only if Q. And this is basically, technically, this is of course shown by this notation. You can write this as Q only if and only if R, and you can write this as R if and only if Q. Any of these would be right. Meaning that you would rephrase this sentence as you watch TV if and only if your mind is free. Okay? You watch TV if and only if your mind is free. Now the next statement that we have is for you to get an A grade. For you to get an A grade, it is necessary and sufficient that you do all the homework regularly. It is necessary and sufficient that you do all the homework regularly. So based on the example that I've seen before, when it says it is necessary and sufficient that you do all the homework regularly, I put this as the first. Basically, I put this, since this is the necessary and sufficient condition, I put it as the first sentence over here. So I write this as you do I don't really remember that example properly. Seems like I was wrong. Okay, so you have to write this as when it is necessary and sufficient that. So this is the necessary and sufficient condition. So it seems that you have to put it as the second sentence, and the first sentence would be this thing over here. So then you have to write, you get an A grade, you get an A grade, you get an A grade. I don't really have enough information to say definitively if that's the only way to write this, but that's the only way that, I mean, we have to just judge these by these examples, and these examples are not rules. You just learn basically a bit here, a bit there, and then you have to somehow put them together. And hope that basically the rules come later. That's basically how these books work. So you get an A grade if and only if you do all the homework regularly. You do all the homework regularly. Meaning that if you do all the homework regularly, you will get an A grade, and you will get an A grade if you do all the homework regularly. It works both ways. But, well, we cannot actually talk about any definitive rules or anything based on examples. Okay, so I was interrupted by some unusual incident, but I suppose we talked about this properly. I don't really know, but basically you write this sentence as you get an A grade if and only if you do all the homework regularly. So it seems that basically you put the necessary and sufficient condition as the second sentence, and then the first sentence, the other sentence comes over here, something like that. But again, we cannot judge based on some single example. So the next statement that we have is if a quadrilateral is equiangular, if a quadrilateral is equiangular, so equiangular means that every angle is, the measure of all the angles are the same in the quadrilateral. Then it's a rectangle, and then then it is a rectangle, and if a quadrilateral is a rectangle, and if a quadrilateral is a rectangle, then it is equiangular. Then it is equiangular. So we have basically two main statements here. A quadrilateral is equiangular, and then the quadrilateral is a rectangle, and a quadrilateral is a rectangle. So we have these two statements here, and here we have, if a quadrilateral is equiangular, then it's a rectangle, and if a quadrilateral is a rectangle, then it's equiangular. So you can say that if a quadrilateral is equiangular, or I'm sorry, you can say that if you take this as P and if you take this as Q, then you can say P if and only if, you can say P if and only if Q, meaning that a quadrilateral is equiangular if and only if the quadrilateral is a rectangle, which is, I suppose, hopefully is what is written here. So a quadrilateral is equiangular if and only if it's a rectangle. Now, question number 5 is given below are two statements. Write the compound statement connecting these statements with and or. In both cases, check the validity of the compound statement. So now suppose that, let me make a new layer here, 387. So that the statements are 25 is a multiple of 5. Statement P is 25 is a multiple of 5, and Q, I suppose, is 25 is a multiple of 8. So of course you know that this statement here is not true, but now we can connect them using and or. So these are two statements, and then out of these two statements, you want to make a compound statement using and or, so you get basically two sentences. So then if you use and, what you will get is 25 is a multiple of 25 is a multiple of 5 and 8. If you use or, so this is your and, if you use or, you will get 25 is a multiple of 5 or 8. So of course in the case of this sentence, in the case of this compound statement, of course you know that the component statements, one of the component statements is actually not true. This one is false. Since one of them is false and you're using and, then you can say that this compound statement is false. Now in the case of this compound statement, since you're using or, and one of the component statements is true, the other one is false, even if one of them is true, then the compound statement will be actually true. So this is true. So the answer here is 25 is a multiple of 5 and 8, and which is false, and the compound statement with or is 25 is a multiple of 5 or 8, and which is true. Now, the question number 6 is check the validity of the statements given below by the method given against it. So for example, let's say that you have you have the statement P, which is the sum of an irrational number, the sum of an irrational number and a rational number, and a rational number, and a rational number is irrational. And you want to check the validity of this statement using the method of contradiction. Using the method of contradiction. Contradiction. So what that means is that the statement that we want to prove that P is true, right? So we want to prove that P is true, meaning that we want to prove that this statement is true. Then we assume that, since we're using the method of contradiction, we assume that this statement is actually false, meaning that I assume that basically P is false, or I can say basically not P is true. If P is false, that means that not P is true. Now, if not P is true, what that implies is that basically the sum of an irrational number and rational number is rational, right? So basically not P not P becomes the sum of an irrational number and irrational and rational number is rational, meaning that you would say is not irrational, then that would mean that it is rational. So now so what this means is that I don't know how to represent an irrational number mathematically. We need to take a look at the solution. Let me take a look at the solution. I'll come back to you in just a few moments. Okay, so now the way that you can write this mathematically, because since of course you have to prove it, so you have to be able to write this mathematically, meaning that you want to assume that the sum of an irrational and a rational number is rational. So so then you can say that the sum of an irrational number and a rational number, you can write it as the square root of a, for example, plus b divided by c. The sum of these two numbers is going to be equal to a rational number, which is d divided by e, for example. D divided by e, where square root of a is irrational. The square root of a is irrational, and B, C, D, and E. B, C, D, E are integers. Okay. Now, what we want to show is that basically we need to somehow create some sort of contradiction. And what you can do is that if you rearrange this term, move it to the other side of the equation, you get the square root of A is equal to D divided by E minus B divided by C. So of course this is going to be a rational number, and it's equal to an irrational number, which is a contradiction. Therefore, you can say that our assumption was wrong. And therefore, since the assumption was wrong, meaning that, therefore we can say that the assumption basically that not P is true, this assumption is false. Meaning that and the logical conclusion is basically P is true. And that's basically what we wanted to show here. So that's actually, well, I mean, very interesting way of proving anything really. It's very concise and elegant. Now, the second part of this question is basically a statement that says if n is a real number with n greater than 3, if n is a real number with n is greater than 3, then n squared is greater than 9. This is the statement by contradiction. So the way that we can use contradiction to prove this is that you have to assume that basically the negation of this statement is true, meaning that you have to assume that not Q is true. Now, not Q is if n is a real number with n greater than 3, then n squared is less than 9, I suppose. That n is a real number with n is greater than 3, but n squared is greater than 9 is not true. That is, n is less than 9. Okay. So then basically not Q would be if n is a real number and n is greater than 3, then n squared is less than 9. That's the statement that we have. We want to prove this. So then you can start from this side of the equation, or this side, basically this statement here, which is n is greater than 3, and raise both sides of this to the second power. You would get n squared is greater than 3 squared is greater than 9. Now n squared is greater than 9 here n squared is less than 9, which is a contradiction. which means that our assumption was wrong, meaning that the assumption that not Q is true, the assumption that not Q is true is false. Therefore, so when not Q is true, basically when this statement is false, that means that Q is true. Therefore, Q is true. Let's see if that's actually. Okay, so that's basically how you, for example, how you can prove this. Now the next question that we have is write the following statement in 5 different ways conveying the same meaning. This is an if-then statement. If a triangle is equiangular, if a triangle is equiangular, then it is an obtuse angle triangle. Then it is an obtuse angled triangle. Of course, the statement is not true, it is false. If a triangle is equiangular, then it is an obtuse angle triangle. That cannot be, because then your triangle becomes a 60, 60, 60, and it becomes an acute angle triangle. All of the angles are 60 degrees. But that's not the point. Basically, the point here is to write this in the form of in 5 different ways. And so what you can do is that a triangle is equiangular. You can take this as P. Then this statement, you can take it as Q. So you have if P, then Q. Which means that basically P implies Q. P implies Q. Now what you can say is that basically P is a necessary condition for, P is a sufficient condition for Q. You can also say that Q is a necessary condition for P. You can also say P if only Q. And there is one more thing that you can say. There was one more thing here, okay, so you can say that P is sufficient condition, P only if Q is necessary, and not Q implies not P. Not Q implies not P, which is the contrapositive of that statement. So what that means is that, for example, this one over here, it says P is a sufficient condition for Q. That means that if a triangle is equiangular, it's sufficient, if you know that the triangle is equiangular, it's sufficient to conclude that the triangle is an obtuse angle triangle. This one over here, Q, is a necessary condition for P. That means that basically if a triangle is equiangular, it is necessarily an obtuse angle triangle. This one over here, P only if if only Q, that means that a triangle is equiangular only if it's an obtuse angle triangle, and not Q. Then not Q implies not P, means that if a triangle is not an obtuse angle triangle, then it's not equiangular. So that's basically that. So a triangle is equiangular implies that it's an obtuse angle triangle. A triangle is equiangular only if it's obtuse angle triangle. For a triangle to be equiangular, it's necessary that the triangle is an obtuse angle triangle. Necessary. Okay? And for a triangle to be obtuse angle triangle, it is sufficient that the triangle is equiangular. And if a triangle is not obtuse angle triangle, then it's not equiangular. So that's basically, that means that basically we have understood this chapter. I was not really sure that I would understand this chapter properly, but it seems that, and it's been always the case for me at least, as I go through these chapters, sometimes in the middle you have the feeling, or you have the kind of logical conclusion that, well, I'm not following, or there is something wrong, or something like that. But somehow, I've mentioned this before as well, the flow of material in this book is seems to be like something very magical, I would say. You wouldn't think that basically going through all of these examples, some here and there, something coming from here, something come from there, that you would actually understand the concept. But it happens all the time, really. I find these books actually really, really, written really well. Okay. Now the next thing that we have here is basically the next part of this book, the next chapter, which is I suppose this was chapter, I don't know, was it 14? Yes, this was 14. So chapter 15 is the statistics. So in the next video we have this chapter on statistics, and so I will see you in the next video with the statistics. Thank you.